All right, so this is recording now. Yeah, so anyone still joining, just, pause the video and write this all down. All right, so we're specifying our area based on the maximum force, right, which is the force in section AB. So this section of pipe is seeing the most stress, and we can come up with an area. Our area is going to be the force AB, I should have put a period here, divided by the allowable stress, right? We were given a stress for this, and maybe I should specify shape and dimensions, loading. We were given the type of load and the material and fabrication. We're sort of loosely following this. We don't know, well, we know we're given the material, so we're going to look this up in a table. Let's see if there's a better one for this. Magnitude, material. No, these are kind of loosely, these rules are kind of generic, so we have to find the force, right? So we have to find the actual loading. And we don't need to specify a design factor because we're given the maximum stress that we're required to be under, right? So we're given a design stress. So we skip this stress, we basically skip this step because we know our design stress in this case is 18,000, is it 18,000? 18,000 PSI. So now we're writing the equation for the expected maximum stress, except we're writing it the other direction. We're solving for the area. I mean, you can write this out and realize, yeah, I need the area. So the max or the allowable is under here. So my area is going to be the 16,356 pounds divided by the 18,000 pounds per square inch, right? And this gives me an area of 0.909 inches squared. All right, so I'm going to go PowerPoint here. Yes, I did. All right, table A9. We were told that we need to use a steel pipe that is standard Schedule 40 steel pipe. So if you go to table A9, you see you've got properties of steel pipe and mechanical tubing right up here. Table A9A is actual pipe standard sizes, right? You can see here nominal Schedule 40 pipe size. And the first thing we're going to look at is we're going to look for an area that's greater than or equal to 0.909 square inches, right? We don't want the stress to exceed 18,000 PSI. So we need to find an area that is at least 0.909. So if I go down this column, right, I see, oh, okay, here's one. Now 0.909 falls in between these two values, right? So, but this is a perfect example of, this is choosing off of a list of available materials, right? The smallest available pipe that does this job is pipe 2 standard. So this is a 2-inch Schedule 40 pipe. You don't have to calculate the area based on the OD and ID. You just look this up in a table. Oh, look, the area is 1.075 square inches, right? That's one reason they tabulate this area, so that you can look and find the area you need for applications. Because these pipes are used for such a wide variety of applications. So here we've got 1.075. So we're going to go back to our screen here. table A9. So let's see. We found a pipe with area of greater than our 0.909. We have choose a 2-inch schedule 40 pipe. And the area is, I believe it was 1.075 square inches. Yep. All right, so now, oops, we can find actual elongation, right? So the first part of this problem was just choosing the right pipe that we need to use in our application to keep the stress below 18,000. Now notice, we do not use this area, right? We use the new pipe. This is the area we use. This is the area of interest for us to find actual elongation. I can't tell you how many times people would solve a problem and they'd come up with an area and they choose the area that they needed, and then they do the subsequent steps with the old area. No, you need to use the pipe that you're choosing, or the item that you're choosing. So let's start with, let's just write an equation out here. We've got the delta. Remember, the delta is this elongation. So the elongation at C, total deflection of point C, this is going to be a combination, right? This is your total deflection. This is a combination of the AB section plus the AC section, right? So that's how we're going to break this down. We're going to look at the forces and the area in AB, and then the forces in the area in AC. Now the area is going to be the same, but notice, right, we've already calculated the two different forces above. For the AB section, I'll write out the equation here again so you recall it. We've got the force we got the force in the AB section, the length of the AB section, right? So only the AB section. I don't know why I put the AB here. The area is constant through both sections. And then E is the Young's modulus. We're using steel, and I'm trying to remember if the Young's modulus is shown in your pipe table. I think it's just, well, it's coming from A10. Let me go to the pipe table just to make sure. A8, A9. Let's see. A9, A9. Does it have the modulus? No. So you're going to have to get that from A10. That's the modulus of steel. Let me write this down. E is going to be 30 times 10 to the 6th PSI. All right, so we can fill this table out. We've got 16,356 pounds. Our length, well, let's look at what units we're going to be working in. Our area is in square inches, right? 1.075 inches squared. I'm just going to convert this 4 feet to inches. You guys should be able to see that, right? 4 times 12 is 48 inches. Let me just make a note, 4 feet. I think you guys all know this. And then Young's modulus is 30 times 10 to the 6th PSI. And here we wind up with 0.024 inches. This is the elongation that this force over this length on a pipe with this stiffness and this cross-sectional area causes. And then we're going to do the same thing for the BC section, except in the BC section, we've just got the 2,500 pound force, right? Oh, I never finished my subscripts here, BC. So in the BC section, it's only 2,500 pounds. So that's what we have up here. Our length is 3 feet, so that's 36 inches, right? 3 feet. And then our area is the same thing, 1.075 inches squared. And our stiffness, 30 times 10 to the 6th PSI. And here we get a 0.0. I rounded to 0.003. I think it's like 2.8 or 2.79 or something. I have some notes scribbled here. So that's the elongation of just that section. So now we have to add these together, right? So the total elongation is just the 0.24, or sorry, 0.024 plus 0.003. Let's not forget our units here. 0.027 inches. So this is how much we can expect the bar to elongate just based on the applied loads it has. So we broke it down into sections. We looked at each section independently, calculated the, well, we found the area we needed based on the force, allowable stress, and then we figured out the length of each section. So that's how you do this problem. Are there any questions about this specific problem? All right, let me let's see where it's. Oh, yeah. Okay, I'm going to go back to the slides for a minute. I don't remember if there's a few slides in between. Oh yeah, there's. All right. So we talked about elongation here due to loading, right? The other thing that happens is elongation due to temperature change, right? Or deformation due to temperature change. I think probably most people are familiar that if you heat up metal parts, right, they'll expand. And if you have unrestrained expansion, right, so you just, I don't know, where'd my paperclip go? I had a paperclip there somewhere. I don't know. If I heat up this this pair of scissors, which you can't see, you know, it's unrestrained, right? It's standing there in midair. It's going to expand. But if I have a part that's restrained, right, at both ends, and I heat it up, you're going to start causing stresses to build up in the material. So we need to be able to calculate a change in length and then relate that back to a stress. Coefficient of thermal expansion or change in length is fairly straightforward. I have the units here. Oh, here it is. Coefficient of thermal expansion, right? This is a property of the material. This is basically how much does the material change in dimensions per unit change in temperature. And you got to be careful. There's there's different numerical numbers depending on if you're using Fahrenheit or Celsius, right? Let's see, I think, oh, okay, there's a table in the, I'll show you on the next page. So if you're working in degrees Fahrenheit, it's inch per degree Fahrenheit, or millimeter per degree Celsius. And my equation got boot it here to the next line. I'll just do that. So your change in length, right, delta, is just this coefficient of thermal expansion, right? How many millimeters per millimeter per degree Celsius times the original length, right? So notice, the longer an object is, the more it's going to change in length, right? As you heat it, assuming you heat it up uniformly. And then delta T. Your book, for some reason, uses a small t for temperature. Everywhere else, a small t is time, but here it's temperature. So, and this is your temperature change, right? And you can see the units. This is a unit of temperature, or degrees C, or Fahrenheit. This is a unit of length. And then the alpha, you're going to be left with units of length here. Oh, the text, 3.4 and 3.5. Let me, yeah, in your textbook, there's tables that have coefficient of thermal expansion. 3.4. Oops. Let me put this down. Yeah. Here's 3.4. And you'll see something similar in 3.5, right? But for example, steel, and notice the two different numbers, right? This is why it's important to make sure you know what units you're working in. Let's see, gray cast iron, right? 6.0 times 10 to the minus 6 per unit Fahrenheit, right? But if you're working in Celsius, you got to use the 10.8 times 10 to the minus 6 per unit Celsius. So be careful which one you choose. Here's more, table 3.5. These are plastics. All right, so I have a problem to work on here. This one's really quick. Oops. Oh, my desk is drowning in notebooks. I'm just going to put this over here. All right. Yeah, I made a mistake here on the handout. It's actually example 310, page 161. You have a push rod in the valve mechanism of an automobile engine, and it has a nominal length of 203 millimeters. So you have this rod. It's made out of SAE 4140 steel. Compute the elongation due to a temperature change from minus 20 to 140 degrees C. So apparently we're going from, like, I don't know, Alaska to maybe Death Valley here. Oh no, this is Celsius. This is crazy. This is not even, so this is a push rod. It's just the engine getting hot. All right, so let's see. We've got this rod, and it's, I'm just going to draw a generic length. Well, I better draw it with corners with a nice sharp length here. This is 203 millimeters. And we want to find what the elongation is due to temperature change. So our delta is just going to be the coefficient of thermal expansion times the length times the change in temperature. So we know the length is 203 millimeters. Delta T, well, I'll get to delta T when we write it, or when we get there. Let me show you the table this is coming from. So if I go to table 3.4, and I'm using SAE 4140, they're all the same. It looks, oh no, they're slightly different. SAE 4140, right? I go across, I've got 6.2 times 10 to the minus 6th. For Fahrenheit, but look, I'm working in Celsius, 11.2 times 10 to the minus 6th per degree C. So this is alpha, 11.2 times 10 to the minus 6th. And we can put units in to remind us, millimeter per millimeter, degree C. So our delta here is, write this out, 11.2 times 10 to the minus 6th millimeter per millimeter degrees C. Our length is 203 millimeters. Our delta T, what is our delta T? Our delta T is the difference in these temperatures, right? So we've got 140 degrees C minus a negative 20 degrees C. This is important. Don't just take 140 minus 20. You'll get 120. You're actually taking 140 minus a negative 20, right? It passes through the 0 point. So we're basically adding 20 degrees to this, right? This is a plus. A minus and a minus is a plus. So this is 160 degrees, right? I think this is probably the most common mistake I see on these temperature problems is using the wrong DT. So what do we got here? We've got a delta is, you plug in all these numbers, you wind up with 0.364 millimeters. So that's how much this rod is expanding. So I mean, not very much, right? 0.3 millimeters over 20 centimeters. That's pretty small, right? Here's what's 20 centimeters look like. Yeah, so 20 centimeters is like the little less than the width of this paper. And you're basically expanding, you know, close to half of one of these tiny increments. All right, so that's thermal expansion. Let's go back to the slide here. Do we have enough time to do this problem? We would have if I didn't talk so much. Yeah, so you may have hot structural components that are now restrained on either end, right? So if you have restrained expansion, you basically wind up with thermal stresses, right? You look at, all right, if this was to lengthen due to temperature change, this is the elongation you would get, this delta, right? Which we just calculated for the rod. Now, unit strain, right? Remember, strain is the change in length divided by the original length. If you put these two equations together, right, you see that strain is basically alpha times the change in temperature, right? The L's cancel out. And we can relate strain to stress through Young's modulus, right? The stress is just Young's modulus times the strain. This means that if we heat something up and it's going to expand, it's going to elongate a certain distance, right? If it's restrained, it would have elongated that distance, but it's generating a strain instead, right? And that's going to generate a stress. So we can get our stress by knowing, okay, the Young's modulus of the material times the coefficient of thermal expansion times the change in temperature. Yeah, so this is an example. Steel structural member in a furnace is made from SAE 1020 steel, and it undergoes an increase in temperature of 95 degrees F while being held rigid at its ends. So we're going to compute the resulting stress in the steel. We can get through this problem and then we'll end here. All right. So the stress, remember, stress is Young's modulus times alpha times dt, right? And this comes from the relationship of strain, right? The Young's modulus for steel is 30 times 10 to the 6th psi. We're working in this problem, we're working in English units. And the delta T is 95 degrees F. And the alpha is 6.5 times 10 to the minus 6 degrees Fahrenheit minus 1. This is from table 3-4. This is the same table we've used in the last problem, except now it's in It's not in metric, we're taking the Fahrenheit units. All right, so our sigma is just equal to, we got 30 times 10 to the 6th PSI. That's the stiffness, right? Our alpha, 6.5 times 10 to the minus 6 degrees Fahrenheit, minus 1. Oh, I should have written this out with, let me write this out in units. I'm going to write inches over inches, degree Fahrenheit. And then you've got 95 degree F. Right. This time you were just given the temperature change, 95 degree F. Notice, right, the Fahrenheit cancels, and the pounds per square inch, yeah, is going to give you a cancellation as well. Let me just rewrite this as a unit here. This is pounds per inches squared, right? You're going to wind up losing inches on top, the inches on the bottom, but you'll wind up multiplying again by inches. So you'll wind up with square inches. So this is why you don't necessarily have to include the units on this, but I was doing it just to kind of show you where we were or what you get. So you wind up getting here 18,525 PSI. Did I write this down correctly? The 6th? Yeah, that is 10 to the 6th. Let me just check something here. 30 times 6.5. Oh, yeah, that's right. Times 95. Yeah. All right. So this is our stress. Compute the resulting stress in the steel. So now, one thing they'll notice here, this is the stress in the steel. If we look at from table A-10, right? I'm going to look at SAE. And this is kind of above and beyond what the problem is asking, but I want you to see. So now we can look at table A10, and we can find SAE 1020 steel. In the weakest form, let's see, the yield strength in the weakest form is 43, right? So we could say it should be safe from yielding. Oops, I'm buzzing here. We don't actually know. Let me just make some comments here. So from table A10, SAE 1020 steel has an SY equal to 43 KSI. Let's just put at its weakest. Oops. So this should be safe from yielding. But this is in compression, right? In compression, this should be checked for buckling. And this is not something we're going to cover until chapter 6 and 11. I don't even know if we'll get to 11, but chapter 6 is buckling. So the point here is that we've got this stress, 18,525. Physically, we know this is in compression, right? It's being held rigid at its ends. It's undergoing an increase in temperature. So All we can say is that we need to actually check this thing for buckling because we don't know for sure. But it should be fine from yielding. So in terms of tension, right, it would be well below its yield strength. So that's thermal expansion and the stresses it can cause. And let's see, we've got a few more examples to do here. What else do we have to cover? Thermal stress. We just did that. Oh yeah, stress concentration. So we'll do this on what, Wednesday. We'll continue on. All right. So that's all I have today. Looks like my video locked up for some reason. What happens if I do this?